Hi everyone, now let me introduce our work, Lightning Every Darkness into Peers, a calibration-free pipeline for raw denoising. As stated in title, our work mainly focuses on low-light raw image denoising. Now, let's start from several background knowledge. Due to tractable primitive noise distribution and higher bit depth for differentiating signal from noise, raw images are preferred in several scenarios. Previous work SID focused on real noise-based method. Nevertheless, the difference between sensors should be considered, so dataset recollection for each sensor is required. Due to high cost of recollection, simulating real noise pairs with a noise model is considered in denoising process. For instance, existing SOTA methods are all based on calibration. In detail, such methods contain three subprocesses named preparation, calibration, and training. Firstly, a predefined noise model should be designed and data collection should be done. Secondly, parameters of noise model should be estimated for exact noise synthesis. Finally, it utilizes synthetic data to train the network. Nevertheless, calibration strategy has several disadvantages. For instance, it is time-consuming and labor-intensive, and neural networks are tightly coupled with the target camera sensor, so retraining is required for each camera type. Moreover, only synthetic noise is involved in training process, so it cannot generalize to the part outside the noise model. Based on the observation, we aim to simplify calibration, generalize to out-of-model noise, and rapid deployment. Thus, we propose LAD, a simple calibration-free pipeline for low-light raw image denoising. As stated above, we only need 6 pairs of data and 1,500 iterations to reach the SOTA performance in 2 raw-based denoising datasets and 4 different camera models. The log fields in these 2 images show the comparison between ELD and our method. To be more specific, PMN's training strategy takes nearly a full day, where ours only needs 4 minutes. Here is our calibration-free pipeline, referred to as LAD. Similar to the calibration-based methods, we first predefine noise model phi and random sample noise parameters as virtual cameras. Secondly, we pre-train the network with synthetic noise. Immediately afterwards, few-shot pair data with target camera needs to be collected, and we use it to fine-tune the network. Here is a flowchart of LAD. More specifically, we introduce camera-specific alignment for each virtual camera in pre-training process. After pre-training, we average the weights of all CSA to be a single one, combine it with convolution to form IMNR, in-modal noise removal branch. Plus, we add an out-of-modal noise removal branch to tackle out-of-modal noise. Two-step optimization are introduced in this period. Now we show the schematic diagrams for deployment. Taking advantage of the additivity of linear functions, we combine the IMNR and OMNR into a single convolution after the whole optimization process. Here are several visualization results for out-of-model noise and the denoising results in different methods. The most important thing is why we choose 2 pairs for each ratio to fine-tune the whole model. According to the ablation studies, we found that 2 pairs of data are enough to get a huge performance improvement, but further adding data doesn't significantly improve performance. Around this point, we proposed a discussion. As stated in preliminaries, the variance of noise is log linearly related to the overall system gain. With only 1 pair of data, it is impossible to find the correct linear relationship. Plus, utilizing 2 or more pairs with similar system gains cannot model linear relationship precisely due to the non-negligible error of the sample scope. Thus, we adapt 2 pairs of marginally different system gains to model the relationship. This also supports our design of each component in the training process. And that's all. Thank you.